Good evening, ladies and gentlemen. My name's Ralph Rayner, and it's my pleasure to introduce this evening's speaker. A few words of background and introduction to the Stanley Gray Lecture. The IMarEST Stanley Gray Lectures and the annual Stanley Gray Awards are named in memory of Stanley Gray, who was the Chief Mechanical Engineer at the Port Directorate of Basra during the 1950s and 1960s. When he died in 1973, he left half his estate to be held by the Institute in trust to create the Stanley Gray Fund. He expressed the wish that the money should be awarded via a scholarship or prize to wherever the Institute saw distinction in marine engineering. The remit has since been expanded to cover marine science and technology. The Stanley Gray series of prestige lectures, launched in 2002, is held to mark his generosity to and patronage of the Institute. And so to this evening's speaker, I'd like to introduce Dr. Graham Brown. Graham is currently Divisional Director, Oil and Gas at Sonardyne. He has more than 20 years of experience in designing and delivering subsea instrumentation and communication systems to the oil and gas, defence, maritime security and oceanographic markets, covering all water depths from the shore to the bottom of the Mariana Trench. Starting out as an electromechanical engineer, Graham has been involved in the design and installation of instrumentation systems from high-level system engineering to the fine detail of transducer design. Graham is a Fellow of the IMarEST, a Fellow of the Institute of Directors, and a member of MTS and SUT. I invite Graham to present his lecture, Can Marine Autonomy Save the World?
Thank you for those kind words of introduction, Ralph. And I follow perhaps a decade after you giving one of these lectures. And I also feel slightly awed to be up here because of the quality of people that have come before me. Me as a mere industrialist rather than an engineer, rather than some of the quite serious scientists and technologists that you have come to talk to before. So I hope I can do the lecture justice this evening. So, can marine autonomy save the world? Well, I'm going to give you an overview of some marine autonomous systems, what I think about marine autonomy, where I think it's going, and also some insight into an important project that's on the way in the UK. But first, I want to have a little think about legacy. And so, Ralph's already explained about Stanley Gray. Stanley Gray, who I have quite an affinity with because I was once a chief mechanical engineer, as was Stanley, in the port of Basra in the 1950s and 60s. So I want you, in terms of legacy, just to think about Basra. What image of Basra do you have in your mind? Well, I'm certain that it's not this one. When Stanley worked there, Basra is known as the Venice of the Middle East. Elegant ladies dressed like Audrey Hepburn would descend from propeller-powered planes and go and tour the canals of Basra. I'm certain that's not the image that you held in your head. However, Stanley probably does have some legacy. And in the port of Basra, some of the structures, and I think these are probably of the age that he would have worked on or been in place, are still in situ within that port. So it caused me to reflect on what would my legacy be. And so when I'm here tonight and I look at this fantastic audience that we've got here, of people at very different stages in their careers, hosts of people from the universities from around the world, welcome to the UK, in the human-powered submarine competition. Absolutely fantastic to see you here at the start of your careers. And also, today there's been an IMarEST meeting of operational oceanographers. Perhaps some of those towards another end of their career. And of course, I can see some local branch members, so we have the full gambit from those just starting to those that have probably retired. So what will my contribution be as I sit here in the middle of my career? So, on to the bigger picture. What does the world need saving for? And some of you may not agree with the science, there are people that disagree with this type of science, but most engineers and scientists probably don't. So, in the words of Al Gore, carbon dioxide, an inconvenient truth. The temperature of the northern hemisphere correlates very well with the atmospheric concentration of carbon dioxide. By the summer of this summer, 2016, we're now up to 405 parts per million, and it's climbing more steeply. Politicians and scientists around the world who work on this project have recognised this, and we are starting to take action. COP21, the climate accord in Paris last year. We are going to take action to try and limit emissions to try and keep global warming to around about 2 degrees C. But this has some very, very significant implications for all of us about how we live and how we use energy. So, how much carbon dioxide is there around in the atmosphere? Well, aside from all the natural biological processes, about 1,000 gigatons has been added over the 150 years of the Industrial Revolution. And we started this here in the UK. In the last 15 years, we've added another 500 gigatons. And gigatons is an unimaginable number. The scientists tell us that we have perhaps 335 gigatons still to go. And we're emitting 36 of those every year. Left in the ground is lots of hydrocarbon. And we're going to extract that and we're going to burn some of it. And there's actually probably a lot more fuel left in the ground that we could burn. Just in the UK, for example, deep coal underneath the North Sea, there may be more than 3 trillion tonnes of coal still left in the UK. Is that fuel going to be taken out and burned? No, not immediately. But we have plenty of energy. Our question is how we use that energy sensibly. And how we use it very much depends upon where we live. In the United Kingdom, typically every person in the United Kingdom contributes 6.5 tonnes per year. But of interest to the IMarEST might be the fact that international shipping is actually the 8th largest country. The UK, being the globe's 5th largest economy, is actually the 7th largest emitter of CO2. America, the rapid industrialisation of China, the development of India, and over time, the growing wealth and standard of living for everybody on the planet will mean that we will be burning more hydrocarbon fuels. And we've got to do something about this. Hopefully this slide is clearer on the screen as it is. Carbon we put in the atmosphere already is likely to contribute to, we're already in almost 1 degree C temperature change. If we're going to hit the 2 degrees C safe limit by controlling our carbon emissions, then interesting things are going to happen. We're still going to have some melting of the ice caps. Sea levels will rise by 1 metre. It will start to threaten some coastal large cities, such as Amsterdam, such as New York, even London. And of even more concern, perhaps, than the impact that we have on ourselves, is the impact that we have on these delicate marine ecosystems. There's already plenty of good science to show bleaching and slowing of growth of corals. But the wider impact on broader ecosystems and what that will do to us is very significant. And if we keep pushing on emitting carbon, we'll end up in a situation where we'll cross over a tipping point. And we need to talk to true climate scientists to understand the impact of that, but it's not going to be pretty. So 36 gigatons. How can we put that into context? Well, for the 6.5 tonnes per year of CO2 emitted for a UK citizen, those 8 fuel tankers there, if they were filled up with petrol, they would represent your lifetime's emissions, about 350 to 400 tonnes of CO2. Just out of interest, you respire, breathe in and out, some 23 tonnes of CO2 over your natural lifespan, and unfortunately, out of a slightly different orifice, another 8 tonnes comes. But talking about Paris again, there are some significant implications. This is the slightly larger petrol tanker that you'll see on the UK road. This is the type of thing that generally delivers to a garage forecourt. It's got 40,000 litres, 8,800 gallons on board. If we want to stay under 2 degrees C, and there are about 7 billion of us on the planet, each one of us on the planet has one of those left for a lifetime. That's actually not a lot of energy. So, how can we transition? Well, we're making great strides in Europe and the rest of the world on renewable energy. In this year, the investment in upstream oil and gas equalled, or was the same as, the investment in renewable energy. So very, very rapidly, our energy mix is changing. But for transportation and for certain other industries, we're still going to be emitting lots of carbon. So let's have a quick look at what carbon capture and storage actually means. For power generation by gas, oil or coal, and also in particular for steel and cement as industries, we can capture those flue stack emissions. By quite complex chemical processes, the CO2 can be scrubbed, it can be compressed, and it can be piped away for storage. And it can be stored, the intention is, for geological periods of time. Now, this is entirely possible because we have the types of stores under our seas, under the ground, where hydrocarbons have been stored for millions of years. So this CO2 can be captured, compressed, and stored. This allows us to continue to burn, certainly in the UK context, gas. Whilst we increase the amount of renewables, we change our energy mix, we become more energy efficient. In fact, the UK has made some tremendous strides on this over the last few years. So, one of the previous UK Secretaries of State for the Department of Energy and Climate Change summed it up like this. Basically, it means we can keep the lights on. And so, if we're choosing how we're going to use energy, we've got to be a bit careful about ensuring that we do so in a sensible manner. So, why am I here? Why am I here as a subsea engineer? I've spent a while prattling on at the moment about carbon dioxide or climate change science. Well, the obvious place for us is to store it under the sea, and this is going on around the world. There are projects in the USA, they're looking at it in Japan, Korea, China, Australia, because, funnily enough, and this is a protest in Germany by Greenpeace, people are not too keen to have it pumped underneath the town that they live in. But 150 miles offshore, into a depleted oil and gas reservoir, or into a saline aquifer, is probably a lot safer and a lot more preferable for most people. However, the environment's not quite so nice. Having been to sea and worked in the North Sea and offshore, and I have been out in weather conditions like that, actually, on naval vessels, that introduces particular challenges, shall we say, to how monitoring systems work and the engineering of the infrastructure. But we've got lots and lots of capacity in the UK. The total storage capacity of the saline aquifers and old depleted oil and gas reservoirs is some 78 gigatons. Now, the UK emissions are about half a gigaton per year. That's everything. We can never capture all of those emissions, but a significant fraction of that could be captured And that means that we've got 150, 200 years worth of storage easily accessible to us. That's more than enough for us to transition our supply of energy. This work was started perhaps more than 10 years ago, and in the previous government there was a programme funded by the Department of Energy and Climate Change where we were going to do 2 FEED studies, and these were to act as demonstrations of commercial viability, and this sets the context of what I'm doing at the moment. These 2 projects are currently cancelled, but I'd like to think that they haven't gone away entirely. So these infographics were produced by DEC and represent the 2 major UK FEED projects. The first of which is the White Rose project, off-sea from Bridlington. It's in a shallow part of the North Sea, and it was going to take CO2 emissions from Drax power station and a cluster of industrial facilities along the Humber estuary and pump it 90 to 100 kilometres offshore and inject it into a saline aquifer. The second one, which was being run by Shell, the Peterhead CCS project, also known as GoldenEye, was going to take the output of a gas-fired power station, hook it to a redundant gas pipeline and inject it back into the GoldenEye field, which has been depleted of gas. Unfortunately, both of these are currently on hold. But there is work underway in Norway, the Netherlands, and there are still some sequel projects progressing in the UK. So what was our challenge? What was my challenge involved in this? Well, funded by the Energy Technologies Institute, and more of them in a minute, my job was to lead a team to look at producing a cost-effective marine monitoring and verification system, the ongoing environmental assessment of emissions of CO2 from the seafloor, to actually enable the deployment of this storage in offshore reservoirs, to make sure that they could meet their legislative and regulatory requirements. Looking a little bit more closely at the functional requirements, what we needed to look at was detect and locate the CO2 in the form they're expected to emanate. That's quite important. We'll talk a bit more about that in a minute. And there's a sort of 3-legged stool for marine leakage, and we'll go into more detail on that. Does it damage the environment? Does it damage the financial success, the commercial viability of doing this? And does it meet the climate change science? The parameters in the third point down just say we need to do it in the North Sea, and we have to sort out CO2 leaks from the store from anything else that might be leaking out the seabed. Damaged hydrocarbon facilities, leaks from natural sources which occur, and the emissions of saline aquifers which actually connect with the seafloor, like the saline fluids. So we're going a little bit more into the team because I'm talking about autonomy tonight, perhaps the autonomy team, but we're certainly not quite the A team like this. It's a rather more mixed bunch of people. Bunches of engineers, scientists and technologists don't quite have the same screen appeal. So, looking at the players in this, shall we say, the Energy Technology Institute in the UK is a public-private partnership, and they've funded hundreds of millions of pounds worth of research and development on a lower carbon future for the UK. The money comes 50-50. 50 from the government, 50% from industry. And the obvious players on the industrial side, the BPs, the Caterpillars, the Shells, Rolls-Royce, etc., have a vested interest in developing these either as store operators or as building a plant that does the capture, for example. The project was run as an open competition, which Sonardyne and FIMarEST run. We worked together as a joint prime contractors. Sonardyne is an underwater technology company, and FIMarEST as an operational company for deploying the equipment. We have been assisted in this by a wider team of scientists at the National Oceanographic Centre, the University of Southampton, Plymouth Marine Laboratory and British Geological Survey. It's worth just a quick look on what the ETI's purpose was. And that was to really prove that we have viable commercial operation of low carbon technologies. And just to finish off the 18 bit, we don't quite look the same. We don't have a black band with a red stripe down it, but we do have these yellow autonomous underwater vehicles, which we load with some pretty good sensors. So, now for the science bit, as they say in the adverts. Understanding marine CO2 leaks. CO2 in a marine system is very complicated, surprisingly complicated. There are many different factors we have to take into consideration. The chemistry of seawater, how it might come out of a reservoir, what form it might appear in, how do the natural processes impact on this, and all of this has to be formed into, we have to have a good understanding of this before we can engineer any form of system to attempt to detect it. So to start with, we have to understand a bit about the geology. The British Geological Survey helps us out here. About 15% of the UK storage capacity is in depleted oil and gas reservoirs, and about 85% of its future capacity is in saline aquifers. Luckily, the North Sea is full of such things, many of which have been found by people looking for oil and gas in the past. So there are a number of different types of geology, and they give rise to different risks of the CO2 being able to leak out. Now, you've got to remember, the geologies that we're storing this gas in, or actually dense phase liquid at this stage, are more than 1,000 metres below sea level. They come with sealing layers in a southern gas field that would likely be a salt dome. But there are sandstone formations which are usable and other sealing geologies. But the gas could come out. So if we were to postulate how it might get out into the seabed, then it might come up a well bore, or it could come up a chimney, a sinkhole, a geological feature that could be tens of millions of years old. It could come up a fault line via a fracture and come out as a linear string of leaks. Or if there's lots and lots of soft, unconsolidated seabed, it could come up a fault line and then come out as many, many, many little leaks. But it's not just the geology we've got to worry about. Me, from an engineering perspective, worries about the mechanical things. These range to different classes of leaks. Ones that can come out at very high pressures, pinholes in pipelines, fractures, damage from ships trawling the pipelines or wellhead infrastructure, or possibly low pressure leaks, a seal that's washed out on a valve stem, as well as these low pressure geological seals. We do have some insight on what might happen as well. There was a scientific program run, led by PML, SAMS, Scottish Association for Marine Science, and some other institutes, not involved as well, which directional drilled under a bay in the west of Scotland, fractured the seafloor, and this was all done under licence, and emitted a few tonnes of CO2 to investigate the marine impact of this. And the type of things that happen, you can see in the picture. You get streams of bubbles, very much like you get from volcanic vents in deep water. You get physical signs, pock marks start to appear in the sea floor. And you get chemical signatures as the gas dissolves into the water, it changes the chemistry. On top of that, much more difficult to see in the underwater photo, you get biological signs. Some species move away from the area. It will kill some species will thrive more in a CO2-rich environment. And that will depend very much on the water depth, the temperature, and the bounding conditions around this. So we've got biological signs to look for, physical signs to look for, chemical signs to look for. We layer another piece of complexity onto this. The hydrodynamics, the ocean processes mixing in from the Atlantic Ocean meeting the top of the North Sea, our rivers dumping nutrient-rich water into the North Sea, the change of the seasons. All of this, with the creepy crawlies in the water and the plants in the water, have a very, very complex biochemical model for how CO2 behaves. So we've got lots of temporal and spatial drivers: photosynthesis, respiration and growth, CO2 exchange with the atmosphere as the wave motion, the wind act, these river processes, and all the mixing that's going on, driven by both weather in the short term and climate in the long term. So hopefully what you're going to see is running is, provided by PML and Jerry Blackburn in particular, a simulation of the change of the pH of the North Sea through the course of a year. If we're going to go and run a mission with an autonomous vehicle to look for changes in pH, as that vehicle is travelling through the sea, every day the conditions that it's trying to hunt the leak in are changing. How do we extract the signal from the noise? And it gets worse than that, because if we look on one day at one fixed instant, and I suggest you look somewhere between Aberdeen and the coast of Norway, you'll see that these two pictures show pH at the surface and pH at the sea floor. They're not dramatically different pictures, but there's a tenth of a unit pH difference there. Then we can start to consider what happens if you actually get a leak. So these are simulations of 100 tonnes of CO2 leaking out of a reservoir in the centre of the picture, same area extent for each of the pictures, but one of them is at the Golden Eye site and one is at the White Rose site. One's in 150 metres of water, stratified, so it's not very well mixed. In the south, much better mixing. Radically different picture that we're going to fly an AUV through or put a sensor on the seafloor to detect. And perhaps to make that a bit clearer, we can look at what happens when a leak evolves. So this is some work done by the Proudman Oceanographic Laboratory, part of MSc, based up in Liverpool. And these are supercomputer simulations. And we read, this is again 100 tonnes of CO2 a day, and how that pattern evolves over the course of a week. The interesting thing is this is showing tidal mixing. And so twice a day the tide moves the pattern around. That pattern is actually useful in helping us to detect and discriminate a biological leak from a man-made leak. We can now start to think about how CO2, what form, phase it's in the water. Here's a bubble being formed. This is work done by ISBR in Southampton. The trace on the right is its sound pressure level, the amount of noise it's making. And that trace is very much like holding a plastic ruler against the edge of the desk and pinging the end of it. Well, as that bubble forms and comes out from between grains of sand or a small chimney, it squeezes its way out and it will ring. We can hear that bubble ring, and you can actually hear that bubble ring tens, if not hundreds of metres away, if the rest of the environmental conditions are right. And it gets more complicated again, because CO2 is absorbed into seawater. So these tiny little bubbles form, they expand as they rise up through the water column, and then they shrink away again. So the plumes perhaps may only rise 2-3 metres from the seabed for most of the types of leaks that we're expecting. And then they will blow around, as in the picture on the right-hand side, in the current. So as a thing to look at with a sonar, quite a complex target to hunt. Now for the legal bits, I'd say, in an advert, and I can't talk very quickly through this. All I really want to say here is there's a complex legal and regulatory framework around how you would operate one of these stores. Yeah, we're talking about putting waste material over the sea for a very, very long time. And there are transnational agreements at the sort of UN type level, which then run down to EC directives for Europe, and then down into UK law. All of which require slightly different regimes for monitoring or planning your storm. So what does this mean? What are we trying to find? Well, how small a leak do we need to detect is perhaps a good question to ask. And back to my requirements, I stated at the beginning. What's sufficient to damage the marine environment, or to jeopardise the financial success, or to meet our climate change objectives? The Crick's experiment did have an impact on the marine environment. It has an impact that was the equivalent to a severe storm. As soon as they stopped emitting the CO2 from the seabed, the local area recovered within a few weeks. But that was a shallow water, warm water site. In the deeper, colder parts of the North Sea, the biological processes in the marine environment is different. And some work is going to go forward with a project called STEM to investigate that. If we look at the geological perspective, those feed studies, feed projects, we're going to put 1 or 2 million tonnes a year stored back into a reservoir. In that sense, they could afford to lose 1,000 tonnes a year and not have any impact on or degrade in any significant way the changing climate that we're trying to enable. So the final thread of it is how would it impact on financial success? And that boils down to how much the regulator might fine you if you had an incident. And you can look up leak data from around the world, but the Frade field in Brazil is probably the world's most expensive oil and gas leak on a per tonne basis. I think it worked out at somewhere around about £100 per tonne of hydrocarbon leaked, whereas in the much more well publicised BP Macondo incident, that was possibly of the order of £50 per tonne. The numbers for in the North Sea are significantly less than that. Check the number there, I'll make sure I've got the right number. So £100,000 per tonne at Frade, £50,000 a tonne at the BP Macondo incident, and £100 a tonne has been the typical level of fine in the North Sea. If you were fined £100,000 per tonne for your leak, you don't have to leak. It puts a price on the CO2. Can you run an effective business doing this? So, onto the system design and conduct. We took the user characteristics from BP and Shell and National Grid and the UTI. We formed it around a technology contract. We looked at the regulatory requirements. We fed into this some science, conducted some proper systems engineering to come up with requirements which cover the concept of operation, economics of commercialisation, the functional performance requirements, all the way down to running some sea trials. And these were delivered for major outputs. A requirement to sense things in landers on the sea floor, an AUV-based aerial mapping system, surface communications, how you get the data back from at sea, and shore analysis and reporting for the operators. So that fits into a sort of system context where we need to look at leaks near high risk points, the wells, survey the wider area, which is a regulatory requirement, and understand what's going on in the environmental conditions. So now we get to look at something that looks like a system. How can we put a system together? Why do we want to use autonomy? We want to use autonomy because it can save us money. It's cost effective. Surveying by ship using traditional methods means you need to put people at sea. You need to get close to the leaks. It's quite complex. We need to fly quite close to the sea floor. So how can we make a system that's capable of persistent surveillance and offer a cost-effective solution in a regime where carbon doesn't really have a high value at the moment? We'll talk a little bit about that later. So, what elements are there? Well, we've got an autonomous underwater vehicle, which is very long endurance, which is equipped with chemical sensors and sonars. We've got landers, which are equipped with chemical sensors and sonars. These communicate to surface assets, and they might be an autonomous surface vehicle, such as supplied by something like ASB, just down the road from here, or via a surface buoy, or via a lower power surface asset, from robotics. We're going to look in a little bit more detail at some of these aspects now. So autonomy, what do I mean by autonomy? In humans, it relates to us making moral, rational choices. I might finish the end of the lecture off with a statement about rational moral choices. But in robotics, it's about differentiating decisions from pre-programmed commands to actually learning about doing something. Can we change the mission on the fly? Is the mission itself capable of adapting to conditions? And again, this drives cost reduction. Humans get bored about making decisions and assessing data. And if systems can learn from that data, then we can get better accuracy in our decision making. And this is funded, this is all founded upon some quite key enabling British technologies. So let's look at the marine robotics, the AUVs, and in particular the surface, the underwater vessel, the Autosub long range from NOC. This is a approximately 3 metre long AUV, but it's capable, with the mission payload that we're putting on it, to operate for approximately 20 days. It's got a capability of going from shore to field to shore, doing the survey that we want to do. And it does this by being energetically efficient. We have to go slowly. And also, as well as going slowly, we've got a very, very efficient power consumption. And that boils down to how we design the system, how we sample the data, what sensors we select. And whilst we're going along, we've got to keep an eye on all the different measurements we're making. We've got to make some decisions. We've got to avoid obstacles, we've got to stay away from things that we don't want to be near. We've got to store and compress the data, and we've got to do this in a reliable manner. To go on it as well, you need to have a fit payload. Fit vehicle, fit payload. Whether that's inertial or non-inertial navigation, tracking, communications with the surface, imaging, sensing, or making sure you rendezvous and go back to where you started. It's all about ultra-low power consumption, intelligent sampling strategies, and integrated sensing. So I'm going to step away from the ETI project for just probably 3 minutes now and talk about a demonstration that was done in the Neutral Buoyancy Lab in NASA of autonomous intervention. And this was done with Saab and with one subsea in particular. And I'm going to show a short video here. Good. So, Sonardyne in space. So this is a neutral buoyancy lab in Houston, and the point here was to do a demonstration of autonomous intervention activities. So, an AUV operating autonomously to provide or do survey tasks, and to make an intervention with a valve, simulation of a subsea valve. So, what we've got in the water, we've got acoustic tracking, we've got optical communications. This is 600, anything up to 600 megabits per second. So we want to run that speed in this tank simulation. And control and communication with the AUV by acoustics. So this is flying around they've taken the space shuttle part of the training pool at NASA, and so they've opened the facility to allow these types of experiments to occur. So this is flying free and is operating completely autonomously. It's going to come across, it's going to do a inspection of the pipeline. So we've got some divers in the tank, so that we're positioning it from the frame off to the left-hand side as it tracks along the pipeline autonomously. Inspection subsea gun. It's now turning around. The blue light is the optical communication system, and as it came into range of the one on the valve station, it picked up to relay the video footage live through water using the optical communications. It's going to come up and dock automatically, and then it's going to actuate the valve. This isn't in any oil field at the moment, but this is something that's going to come to an oil field in the next 10 years or so. Plugged in, special tool, designed from Cyanic, and it's now operating and opening that valve. This potentially, with a little docking station on the sea floor, opens the opportunity for the AUV to go off, be recharged, there it is going back into its docking station, have its battery recharged, and can be sent out to do inspection tasks. But we've got a means of non-contactlessly and wirelessly transmitting the data back into a wired or cabled subsea control system, which means that somebody 1,000 miles away can operate this and get hold of the data. You don't necessarily have to have a ship overhead to do this like that. And so there it is, it's downloading the video that it took of the pipeline, and hopefully it will then replay the jumper. Just a second. And there's the video footage. Come back across. So this was done over 7 days and done as a demonstration to the oil and gas industry at larger in Houston. It shows the type of technology that are going on to these vehicles now, all of which are low. Let's move a bit more into the processing. We need to make decisions. So we're taking lots of chemical sensors, and I'll give an illustration of that in a minute. So we're making electrochemical, spectrometric and optical sensors to make physical sensing, chemical sensing, and we're having to fuse those together, pairs of different sensors, different ratios, to make decisions about, is this a man-made leak, is this biological emission of CO2? And we've got to do that with a particular level of confidence and make sure that we don't cry wolf too often. And so you do that with a suite of sensors, which have fully both co-registered with the navigation data in the AUV and co-registered with the sonar information, process that on board, and periodically surface the AUV and communicate that data back to shore. And here we've got a human in the loop. But there is the potential to take human out of the loop and make the decision underwater. But for the trials that we're doing at the moment, human in the loop to aid in the decision-making process. So looking at one of the sensors, that's a side-scan sonar with a co-registered bathymetry array. And on the left-hand side at the top of the picture, and shown in the snippet, is a CO2 leak in Plymouth, done during some trials last year. The snippet is actually pulled out automatically. The AUV, the computer on the AUV is recognising that it's got a target, automated target recognition, that looks like a gas leak. And you can see some certain features of that, and perhaps having me tell you this one's a leak, perhaps we can have a little bit of audience participation now. Seeing as we're in the Submarine Museum, perhaps you'd like to be sonar operators for the day, or pretend to be the computer on the AUV. So out of those ones, which ones are leaks? Which one would you pick out to be a leak? So, quick show of hands in the leak, perhaps. So, who thinks number A is a leak? Smattering, about 50% of you. B, much lower, 5% or so. C, we're getting to about 10%. And D, pack about half of you. Asking the audience works in this sense, but perhaps not quite the confidence interval you need to in real life. A and D are leaks. And the reason you can tell that they're leaks is they're casting shadows from the sonar imagery. So the picture at the bottom shows the part of the automated target, and it's put a red bar over in the snippet where it thinks the shadow is. B is a shoalfish, and C is the wake of a high-speed boat that's come across the top of the sonar as it's been tracked past. You can see the sort of ripple artifact. So what can you see? Well, the height of the shadow tells you something about the height of the leak, and also they show slightly different patterns, A and D. A and D are taken at different states of the tide. So the tide was running quite strongly for snippet A, and the leak, the image is showing the bubbles blowing off, very much like that picture I showed a little bit earlier in the talk. Whereas in D, the bubbles have risen up through the water column almost vertically. And so you get a much brighter point cloud, but you still get a very, very well-defined shadow. In the seabed landing situation, we're doing pretty much the same thing. But we're taking either an active sonar or a passive sonar to listen to the bubbles, and processing it again together with a number of chemical and physical sensors, and then communicating that detections and data to the surface using acoustic modems up to a surface asset, be that a boat, be that a data buoy, be that an autonomous surface vessel. So again, looking at one of the detection sensors, something we call Sentry IMS, but it's effectively a sonar, an active sonar, sends a beam of sound out and looks for the reflection back from the bubble cloud in the water, and we can detect quite small leaks of CO2 with this. And just to put that into context, behind you, you can probably see the Spinnaker Tower, and this picture shows a sort of overview of where we are. And the dot in the centre is where we are tonight in the Submarine Museum. And well out into the bay behind you, we would detect a 2 litre per minute CO2 leak in 10 metres of water at 850 metres of range with a sensor that can see the light when it's switched on. It gives an ability from a single point location to monitor a very, very large area. Fuse that together with the chemical sensors and you start to build a layer of being able to exclude false detections. So, moving on, is it cost effective? Well, that sort of depends. Is it cost effective is how long is a piece of string? And that depends upon what the regulator in the end says. The regulator will define how much of this monitoring has to be done. It's likely to need a lot of monitoring for the first few schemes, and as confidence grows, less monitoring. However, this is a different technology under different laws of hydrocarbon work. The UK project target that we were set was to come in under 50 pence per tonne stored. And we've got a range of solutions that would do that through the life of the field for the period that it has to be done, less than that value. So yes, you can do it economically. But we do have some challenges. First and foremost, we've got lots of complicated computer models, which we're going to check the proof of the pudding next year in the water. There are very, very, very few oceanographic measurements series of pH and the type of parameters, phosphates and nitrates that we need to benchmark these type of systems in the North Sea. And so the data set that's going to be gathered in summer next year will be probably one of the largest oceanographic data sets of this particular type. We also have some engineering issues, and so endurance. The longer we can make these AUVs operate for, the more cost-effective the system is. We also have to deal with the legal aspects of the operation of autonomous systems at sea. And there are working groups in the UK currently looking at that. But we're very much in a situation at the moment where it mirrors perhaps the operation of hovercraft when they were first came into service, where there was no law for them. And that regulation will develop, and that law will develop, and there are people in the audience who are working on that. We also have to worry about big data. The type of sensing that we're doing is storing megabytes, terabytes of data per survey. We've got to protect that and automate those, ensure that those systems are truly automated. And finally, there's one of economics. carbon has different prices wherever you are in the world. The price today in Europe is about €4.50 per tonne. That's not cost effective for doing carbon capture and storage. But what price do we place on our environment? What price do we place on ensuring that, what price would you place, shall I say, on ensuring that perhaps the world that your children's children inherit is the one that you would like them to inherit? So that puts a view at a much higher level about how we value energy. But the ranges of carbon pricing is quite extreme across the globe. But I think the framework over the next 10 years will see the price of carbon move to a state where these schemes will become financially viable. And perhaps one of my final things is probably the most thing we can't control, or the thing we can control the least, is the politics. I don't have any worries really about the science. We can do the science. I don't have any worries looking out into the audience about whether we can do the technology. There's plenty of young, agile minds, older, agile minds, that are capable of taking these problems on and solving them. I think we can get together at a global level and address some of these problems. We're certainly going to have some short-term problems at a regional level, and the impact of the recent Brexit decision and the fallout from that over the next few months, perhaps years, is going to be quite significant for us. And overall, we really must, as citizens, hold our politicians to account. What is important? Perhaps one of the things that's come out of the UK over the recent period, and perhaps also in the US and France and Germany, is protest politics. Perhaps politics shouldn't be run like Big Brother, but perhaps we should care a bit more about it and be involved in it a bit more and say what we believe and stand up for some things and make sure that our politicians also do so. These programmes are viable, but as long as there's a political will to hold a hand on the rudder and hold the course. Switching programmes off, switching them on, switching them off, is not a viable means to go forwards. So I'll really finish on the words of Gosport. Making predictions is difficult, especially about the future. I remain convinced that the science and engineering are less so about the social and political factors. So thank you very much for listening to me. And do you have any questions? Should come from professional oceanographers. At the back there.
You mentioned early on.
Hang on, I've got a microphone,
Thank you. I really enjoyed your talk. You mentioned early on about kind of an environmental concern of the impact of the leaks might have in the surrounding marine life, and I was wondering if you'd how you're avoiding causing harm to that environment through your persistent monitoring, particularly use of active acoustics.
The type of active acoustics that we're using is not like military or naval sonar, so it's really to do with the amount of power that we put out in sensing and the frequency band that we put it out in. So for conducting this work, we have to comply with UK regulations. We have to conduct environmental impact assessments, and we have to talk with the marine licensing authorities such as the MMO, the Environment Agency, Crown, etc. Also, there's a rigorous process to make sure that a valid environmental impact assessment is done and that it's reviewed by somebody that's not just us.
Thank you. Well, I'm coming back to the beginning of your speech, and there you showed us the world map with our carbon dioxide emissions, right?
Yeah.
And you've been talking about how the first world countries have been actively trying to solve this problem. That being not completely solving the problem, but helping a bit out of it. And then on that map, you could also see that India was also in a critical emission state, and as a developing country, I would assume that they have other priorities for their people than storing up carbon dioxide. Thinking about that, thinking about the resources that's put into this, how do you think the inequality in the efforts, or not balanced efforts, would affect the efficiency of the concept?
Okay, very good question. I think that countries like China are now accepting that they've got to do something. There's actually quite a large US-China program moving forwards. Also in countries such as India, they're also changing for other reasons the mix of energy that they're using. So for example, a lot of coal has been burnt in the past. By switching their energy needs more towards gas, that has a definite benefit. But we have a role in the, perhaps in the first world, in developed countries, to shoulder some responsibilities for this. My personal opinion is we've got to make trade mechanisms and support and funding work for all of our good. It's a natural desire of any country to want to improve the living standards of its citizens, and I don't think we've got any right to turn around to people and say that they shouldn't use energy. But we should try and act responsibly to help them to use energy, and whether that's by joint scientific research projects, whether it's by funded programs, whether it's by overseas development aid. I think that the UK, the European Union, the United States and other players have all got a role to play there. And I think some of those type of negotiations need to come out of that, the UN and COP, the Paris type agreements.
Hi, thank you so much for your talk. I enjoyed it a lot. I want to get a bit more an understanding between the feasibility and the leakage that occurs.
Okay.
I was wondering, what if we reduce the storage pressure? How would this affect the monitoring system, the natural leakage to occur, and eventually the feasibility of the project for different countries?
Okay, you need to transport CO2 as dense phase, which means you've compressed it. It's probably to around about 150 atmospheres or so to run the pipelines at. You then may have to push the pressure up slightly more to inject it. It's under typically a kilometre down, and you'll have to run at a certain pressure to re-inject into either a saline aquifer or into a depleted oil and gas reservoir to start to lift the reservoir again. It will cause the seabed to heave gently. That sounds quite scary, but that type of thing is actually done in the oil and gas industry today for enhancing oil recovery. So these type of processes are actually quite well, some of these processes are quite well proven and demonstrated. They need monitoring, they need careful engineering for, and they need geological risk assessment. But the storage pressure itself is probably not the major concern here. The problems are more likely to occur due to things like chemical interactions of CO2 plus water equals carbonic acid in inverted speech marks, and that can cause corrosion, or it can cause interesting effects with cement that are used in well bores. And so a lot of research work is actually funded. It is focused around making sure that the mechanical and the physical wells integrity is well researched. There's a lot of work going on in the UK university sector on that. At the front, something.
Thank you. I found your synopsis of this lecture very thought-provoking, and one of the thoughts I had whilst I was reading it was the fact that we have a land mass and we have a water mass on this planet.
Yes.
And you have gone very deeply into the water aspects of CO2.
Mm-hmm.
So what my thought is now, most of our pollution and contamination majority of it, I believe, comes from the landmass. But now we are going into the oceans. We are coming up with results of CO2 from the oceans. So, has your company any idea how much CO2 comes out of the landmass on this planet compared to the CO2 coming out of the oceans? I know the ocean is much bigger than the landmass. I think it's 59%.
No, it's much more than that. 71%.
70%. Okay.
It should be called water, not
30% land, 70% ocean, or water. Not ocean, water, all levels of water, lakes. So my thoughts here are, okay, why are we suddenly very much concerned with the CO2 coming out of the water of this planet?
Right.
When over the years we've never been really concerned. All of a sudden we're very, very much concerned.
Right, the CO2 is not coming out of the water, the CO2 is going into the water. So the stuff that we emit out of our cars and out of power stations is going into the atmosphere. The sea has absorbed, or the oceans, the water of this planet has absorbed about 50% of the total emitted CO2 that's gone into the atmosphere. And so it's buffering the CO2 in the atmosphere. By making the oceans slightly more acidic, we've actually got slightly less CO2 in the atmosphere. If it hadn't gone into the ocean, we'd be in even more trouble.
So the ocean is, at the moment, is a benefit to us.
Oh yes, very much so. It's absorbing it, but the problem is that it can only do so much.
Yeah. So you mentioned in your synopsis that you have diversifications of the sea life and ecosystems in the ocean.
Yeah.
These systems that you're talking about, presumably, these are possibly systems that are going to help us in absorbing, if you find them, more CO2. Am I right? More carbon.
That's a very difficult question to answer
At this stage.
And you really have to ask somebody like Jerry Blackford at Plymouth Marine Laboratory on that. However, for example, small shelled creatures, tiny shelled creatures living in the sediment will absorb a certain amount of CO2 until shell. However, if the ocean becomes more acidic, their shell will start to become attacked because of the acidity of the water. So there's
you gain one way, but we lose out on sea life. Yeah.
So that it will impact many ecosystems, which we do not adequately understand. We're playing with a system that we do not adequately understand.
Well, following on this, my thoughts are this, that we are concentrating a lot on the CO2 and storage capacity, which your company, thank God, are there to sort it out for us. But what's happened to forestation?
Again, a slightly wider climate question, and one which I'm afraid I'm not qualified to answer. I said it's one that I'm not qualified to answer. I don't have a developed view on that. I'm not a climate scientist per se. I'm a technologist and engineer working in the field, giving you the lightest of skims over this subject area tonight.
You talked a lot about the way you detect the leaks by looking for these shadows.
Yes.
And cast it on solar signatures. Are you using any techniques of artificial intelligence or machine learning to try and recognise different signatures of different types of leaks, to be able to classify them and grade them? Or is it just purely looking for a shadow to detect the actual leak?
That is one of the techniques that we're actually applying to this problem. So there are all types of image-based analysis techniques that can be applied to look at texture, learning from the images, etc. So I don't really want to say any more about it than that. But I've taken one example to show a method of filtering an image.
And can you just give some idea about, once the leak has been detected, maybe beyond the scope of your project, but then how, in the grand scale of things, are those leaks then dealt with? How are they actually resolved or avoided?
again, there's some insight from that in the oil and gas industry. The one that most people will know the most about, because it's spent a lot of time in the media, was the BP Condo incident. They ended up intervention drilling into the well to plug that particular well to stop the leakage. So there are a variety, if it's a well-based problem, there are certain interventions that you can take. There have been blowouts before where the seabed has been fractured. There are natural blowouts that have occurred. There are different engineering approaches to those, and again, I am not an expert in how that type of engineering work is undertaken. I think in terms of that type of incident, there is some information available from Chevron online about the Flagship incident, which is a completely different category of thing to the BP incident. And there have been many, but it's actually now that things are more openly discussed and publicised, shall we say. Sorry, not a subsea engineer specialist in that particular field.
So, coming to the marine autonomy part of this, and back onto what I think in this crowd is probably a fairly more comfortable area. When you start thinking about how you set up the missions, how you set up the decision making for your AI, so at the moment you're still looking for information on how to make those decisions or what the boundary conditions are to set up a monitoring program for the North Sea, if I've understood you correctly. You're then looking at a variety of different vehicle types and approaches to doing it. And if I've understood correctly, the project's come to an end or has been turned off, as you said. Where's it going next, and how do you make those decisions about your coverage, your autonomy decisions in the next few years?
Okay, so the two UK feed projects to actually capture the carbon dioxide from the power station, pump it offshore and store it into a geological feature, they are basically on hold and cancelled. That was a decision of the Treasury at the last budget. The project that I'm working on is still live, and there is still science and development and engineering work going on because there are other schemes around the world that are going ahead. The Norwegian company Statoil have done a lot of work in this area and have stored a lot of CO2 underneath the Norwegian sector. Not from power stations, but which has been stripped out of oil and gas that they produced and then re-injected. That's been worth over $100 million to them in terms of tax credits. So this technology is happening. Shell are doing it in Canada. There are CCS schemes operational around the world and at different stages. So this is coming along from the projects continuing. And this demonstration project is definitely going ahead still in terms of marine autonomous surveying systems. Now, we're not selecting from lots of different vehicles. We've actually got a candidate system design which is in fabrication at the moment. The vehicle's built, the sensor payload for it's built, the system integration and testing work's going on at the moment, and it's approaching factory acceptance. It will go into harbour trials very early Q1 next year, and then we've got some trials to do in the summer, which I hope to make some both technical publications and scientific publications as a result of. I hope that answers your question.
Brings us to the end of our available time. I have to join you again and thank you very much for the next